Hello students, welcome to the EPG Pathshala. I am Ashok Goyal from the Department of Physics and Astrophysics, University of Delhi. Today in this module, we will discuss the Gram-Schmidt theory, which is an important theory for integral equations. This theory we'll discuss in two parts in this module and in the next module, which form the part of the paper Mathematical Physics. So students, let us see what we are going to learn in this module. In this module, we will learn the Gram-Schmidt method in the context of solving integral equations, and then we will discuss the existence of at least one eigenvalue of the equation. Consider inhomogeneous integral equation f of x is equal to g of x plus lambda times integral a to b of the kernel k, which is a function of x and y, multiplied by the unknown function f of y dy, wherein this gx is a real function, kxy is given and is real, and we will assume it is a symmetric kernel, which means kx of y is equal to ky of x, and lambda is a number, and we have to solve this equation for the unknown function f of x. The Hilbert-Schmidt theory gives an elegant result for the solutions of this equation. Regarding the homogeneous equations, let us consider first the homogeneous version of the equation which we have seen earlier, which is the inhomogeneous Fredholm equation. If we put the inhomogeneous term g of x is equal to 0, then when a solution to the equation of the corresponding homogeneous equation exists, the value of lambda in this case is called an eigenvalue, and the corresponding solution, which is f of x, is called the eigenfunction corresponding to the eigenvalue lambda. We will first prove the orthogonality of the possible solutions of the equation when gx is equal to 0, that is for the homogeneous equation.
Since we are considering a homogeneous integral equation with symmetric kernel, the equation is simply fx is equal to is lambda times integral a to b kxy multiplied by fy dy, where the kernel k is symmetric. So let fpx and fqx be solutions of this equation for the value of lambda equal to lambda p and lambda q respectively. That is, fpx is equal to lambda p into the integral a to b dy kxy fpy, and fqx is also equal to lambda q, the integral a to b fy kxy fqy. Now we multiply this equation or fpq by fq star x, and we take lambda p on the left hand side. So the left hand side becomes fq star fp, both functions are functions of x, divided by 1 upon lambda p is integral a to b dy fq star kxy p of y. Now we take the complex conjugate of the second equation of fqx. So we have fq star x is equal to lambda q star integral a to b dy fq star of y kxy, because we have assumed the kernel to be real also. This complex conjugate is itself. Now we multiply this equation by fpx and take the factor lambda q star to the left. So we get 1 upon lambda q star fq star x fp of x is equal to an integral a to b dy fq star of x into k, which is a function of x and y, multiplied by fp of x. Now these two equations which we have obtained, one equation of a product of the function fq star with fp, another product of the function fq star with fp again, one with lambda p in the denominator, another with lambda q star in the denominator. So we integrate this equation with respect to x. So on the right hand side, we get a double integral, an integral over x and an integral over y. The limits of both these integrals are from a to b, and we use the property that k, the kernel, is symmetric, that kxy is equal to ky, and we can now interchange in the integration variable x and y. Therefore, we obtain, for the second equation, we obtain 1 upon lambda q star, the integral of q star x, fpx dx, is equal to integral a to b dx and integral a to b dy, fq star x kxy fp of x. And therefore, subtracting these two equations, we get 1 upon lambda p minus 1 upon lambda q star and integral a to b of the product of the function fq star x with fp from a to b equal to 0. Similarly, we can integrate the other equation over x and we get 1 upon lambda q star integral of q star fpx dx is equal to the integral over x and y, double integral of the product of function fq star x, kxy and fpy, and again by interchanging the variables, the order of integration can be reversed since the integrals are over finite range. Then we get, using the fact that kxy is equal to kyx, we get now 1 upon lambda q star multiplied by the integral of q star x fpx dx is equal to a double integral or two-dimensional integral over dx and dy over the range a and a to b for both fq star kxy fpx. Now the Gram-Schmidt method consists that all solutions fpm can be normalized, which means that the integral of the product of solutions, so take any solution fpm, normalization of the solution means that integral from a to b of the product fpm star fpm integrated over dx is equal to 1. Now consider the combination fp alpha of x is equal to fp1 of x plus alpha times fp2 of x. Since alphas as yet are constant, clearly lambda p integral from a to b of kxy fp alpha dy can be written as, by substituting for fp alpha in terms of fp1 and fp2, so this becomes an integral, a sum of two integrals from a to b over dy. First integral is the integral for kxy multiplied by fp1. The second one is alpha times the integral of kxy multiplied by fp2. So this we write as fp alpha x. That is, fp alpha is also an eigenfunction with the eigenvalue 1 upon lambda p of the same homogeneous equation. Now integral of the product fp alpha star x fp 1x from a to b is equal to 1 plus alpha times an integral a to b of fp2 star x fp1 x dx, where alpha is equal to 1 upon integral a to b fp2 star x fp1 x dx. But now we choose alpha to be this, so that for this choice of alpha, the integral from a to b of fp alpha star x fp1 star x dx is equal to 0. Why? Because remember, the integral a to b of the product of two functions fp alpha star x into fp1 x is equal to 1 plus alpha times integral of the product of the functions alpha p2 fp2 star fp1. So with this choice of alpha as minus 1 upon integral of product two functions fp2 star fp1, with this choice, then this integral a to b fp alpha fp1 dx becomes 0. And further, integral from a to b or fp alpha star fp alpha x over dx is equal to 1 plus mod alpha square. So that fp alpha x can be normalized by dividing it by 1 plus alpha mod square to the power half. Thus, the M-degenerate solution can now be listed as fp1x, fp alpha x, fp1x, fp2x, fp3x, fpmx. This means fp1, fp2 are orthogonal and they are normalized set of 2 with the rest of the functions being fp3, fpm. The rest of the functions are normalized, but they are not orthogonal to fp1 or fp alpha. Next, we form the combination f alpha 3 is equal to fp alpha 3 plus alpha 2 times fp2 plus alpha 1 times fp1, where alpha and alpha 2 are yet to be specified. Then we have lambda p integral a to b kxy fp alpha 3 y dy we define as f of p alpha 3x, so that fp alpha 3 is also an eigenfunction of the kernel kxy with the same eigenvalue lambda p. We can follow the same procedure as for p alpha. We can choose alpha 2, alpha 1 such that fp of alpha n is orthogonal to both fp1 and fp alpha. We thus have a sequence of functions fp1x, fp alpha x, fp alpha 2, fpmx, where the three are orthogonal. We can indefinitely carry on with this procedure till the mth functions become orthonormal. We thus have the result that irrespective of degeneracies, we can always arrange that the eigenfunctions form an orthonormal set.
Let us talk about the existence of eigenvalues. We first prove that the homogeneous equation has at least one eigenvalue, that is lambda. For at least one value of lambda, the equation has a non-trivial solution, which means fx is not identically zero solution. Now consider the quantity I, which is defined as the product of three functions k xy, f of x, f of y, integral dx dy. Using Schwarz inequality, I is less than or equal to integral a to b of k square xy dx dy multiplied by the integral ab from ab of the square of the function f square x dx whole square. Since we are interested in functions that are bounded, that is integral of f square dx between the limits a to b is less than infinity, we can always normalize the function that fx satisfies, because if they are bounded, then there exists a finite number L, and we can divide the function by under root of that to normalize it. So in that case, fx is normalized, which means the integral f square x dx from a to b is equal to 1. Since the kernel k xy is assumed real and bounded, we conclude that the integral is bounded. We will next prove that the integral can vanish if and only if kxy,
which is also a two-dimensional integral from a to b of kxy multiplied by the product of fx plus f1 with fy plus f1y, then clearly I2 is equal to I plus I2 plus twice times. From this, we can see the I2 is equal to I plus I1 plus twice the integral from a to b over dx multiplied with an integral from a to b over dy of kxy f1x f2i. That is a two-dimensional integral of the product of the kernel kxy with the function f1 of x and f2 of y. Thus, the integral I2 is equal to the integral I plus I1 plus 2 I12. And proving this, we have used the symmetry property. I1, I2, which are quadratic in form, if they vanish, then the integral I12 also vanishes. If we now take f1x is equal to integral a to b of kxy into fy over dy, we get I12 is equal to 0 is equal to integral a to b kxy fx dx multiplied with the integral kyz f of z over dz dy, which is equal to the integral dy from a to b and integral multiplied by the integral of dx a to b kyx fx multiply the integral a to b dz kyz fz, which is equal to the integral dy of a function square of the integral of kyx fx dx from a to b, and hence the integral a to b kxy fx dx must be equal to 0. Because this is the quadratic form, so this has to be 0.
fx so far is completely arbitrary. Thus, the integral from a to b of kxy fx implies that the kernel xy is equal to 0. We thus have proved the result that if integrals of the form I for arbitrary fx vanish, then the kernel kxy is necessarily 0. We now distinguish three cases. If the integral is greater than 0, for all f of x not equal to 0, the kernel is said to be positive definite. If the integral is less than 0 always, the kernel is called negative definite. If the integral can be sometimes positive and sometimes negative, the kernel is called definite. So kernel depends on the value of the integral, whether it's positive, negative.
Kix, that is kn xy, we write as sum over I and j from 1 to Vn of Kijn multiplied by Ki of x, Kj of y, where Kij of n is Kji of n, such that in the limit Vn goes to infinity, Kn xy, which is symmetric, converges uniformly to Kxy corresponding to I. We define an integral In, which is the two-dimensional integral dx dy from a to b of kn xy multiplied by fx and fy. Since In is bounded as proved earlier, it has subject to the constraint of equation given in 9.28. So it has a maximum value I. Then the integral In is written as a sum over I and j from 1 to Vn of Kijn alpha I alpha j. We will prove an inequality which is called the Bessel's inequality. We have the integral dx from a to b of the square of fx minus sigma is 1 to p alpha I kix, which is greater than or equal to 0 for any value of p. Expanding and using the orthonormal property of ki's, this leads to that the integral a to b dx f square x minus twice sum over I to p integral a to b of alpha I ki x fx dx plus sum over I and sum over j from 1 to p of alpha I alpha j multiplied by the integral from a to b of kix kj dx. This is less than or equal to 0, and the right hand side is equal to then integral a to b dx f square x minus alpha I square summed over I from 1 to p is greater than or equal to sigma alpha I square I summed from 1 to p for any value of p. Hence, the integral f square dx a to b is greater than or equal to sum of alpha I square, where now I goes from 1 to Vn. This is Bessel's inequality. Now, alpha i's depend on fx. That is, if fx is multiplied by a number, alpha I gets multiplied by the same number. The left-hand side of the equation is constrained by 1. Clearly, then, the maximum value of In is reached when the alphas or alpha i's reach their maximum possible value. Hence, In equation 930 is to be maximized subject to sigma alpha I square I is equal to 1 to n is equal to 1. I, where k 1n is an undetermined constant, k1n is easily determined using the equation above. The maximum value of In is sigma over I and j from 1 to Vn, Kijn alpha I alpha j is equal to K1n. Let us call the alpha i's which maximize In as alpha I max, then define a function fnx is equal to sum over I or alpha I maximum into Kix. They satisfy the integral a to b dx of fnx kx minus alpha I maximum. We have the equation 9.35 which reads the sum over j from 1 to Vn of Kijn alpha j is equal to K1n of alpha I. Now the maximizing function reads, now this equation when we maximize, then this would read sigma j is equal to 1 to n Kijn alpha j maximum is equal to K1n into alpha I maximum. Now we multiply this equation by Ki of x and sum. The right hand side is then K1 of n sum over I is equal to j to Vn alpha I max Kix, which is then equal to K1 of n Fn of x and multiplied by sum over I and j from 1 to Vn Kij and Kix alpha j max, which is in turn equal to sum over I and j from 1 to Vn Kij of n Ki of x and integral a to b of Kjy Fny dy, which then becomes nothing but an integral from a to b of Kn xy Fny dy.
Hence, f of x is 1 upon K1n integral from a to b of Knxy Fny dy. Fny thus is an eigenfunction of Knxy with the characteristic value mu1n is equal to 1 upon K1n.
We will now discuss the limiting value. The degenerate form of the kernel Knxy in the limit n goes to infinity converges uniformly to k of xy. Hence, the modulus of I minus In square is less than or equal to modulus k minus kn square multiplied by b minus a whole square, which is less than or equal to epsilon square b minus a whole square. Thus, In goes to I as n goes to infinity, because as n goes to infinity, epsilon goes to 0. Hence, in the limit n goes to infinity, the sequence of characteristic values 1 upon k11, 1 upon k12, etc. have a limit 1 upon k1 is equal to lambda 1 and all the k1n's lie below k1. This last statement is because k1 is the maximal value of I and k1n is the maximal value of In. We have thus established that the sequence of function fnx converges to a limit f1 of x and the equation converges to f1x is equal to lambda 1 integral a to b of kxy f1y dy. We have thus proved that for a positive symmetric kernel, there exists at least one eigenfunction f1 of x with eigenvalue lambda 1.
So students, let us summarize what we have learned in this module. What we have learned is that when the kernel K of an integral equation f of x is equal to gx plus lambda a to b kxy fy dy with g kxy the non-functions and the non-function being f of x, when gx, k and f are real and the kernel is symmetric, that is kxy is equal to kyx. The Hilbert-Schmidt theory gives an elegant result for the solution of the equation. When the solution exists, the value of lambda is called an eigenvalue and the corresponding solution f of x is called an eigenfunction corresponding to that eigenvalue. Irrespective of degeneracies, the eigenfunctions can be arranged to form an orthonormal set. For a positive symmetric kernel, there exists at least one eigenfunction f of x with the eigenvalue lambda 1. Thank you.